So today we are discussing about computer organization architecture, module 1, which is basically of machine instructions and programs. So what does this machine instruction and program mean, and what is the importance of this we want to discuss today. The agenda of this session is to discuss on the numbers and arithmetic operations and characters. So let us go into the details. Machine instructions and programs is a part of module 1, and we have two parts in this. The part 1 will be covered in module 1, whereas the part 2 is covered in module. The first topic and today's topic here is numbers, arithmetic operations, and characters. So we know that numbers play a very important role in computing. A number can be a binary number, it can be a decimal, octal, hexadecimal, whatever form it is. And we have to convert these numbers from one form to other, and we have to add them if required, if we have to subtract them if required, depending on the computational requirements and capabilities. So let us see what does this numbers talk about. Let us have an overview of these numbers. So we know that these computers were built with logical circuits and they're going to operate in the electrical form. So which means either they have either zeros or either 1. Okay. For example, in case of a binary number, the number can be represented as an integer or a fractional value depending on the design of it. And the hardware can be interrupted based on an integer or a fractional value, as we discussed. Now, in case of integers, we have a radix point is fixed and assumed to be right of the rightmost digit, and the radix point is fixed. The number system is referred as fixed point number. If the radix point is fixed, we call it as a fixed point number. And if you are trying to represent in terms of sign magnitude, we can represent them in ones complement form or we can represent in two's complement form. And we define the amount of information represented by such a digit as a bit of information, where bit stands for binary digit. So one single value, either 0 or either 1, is called as a bit. That means a binary digital value. Okay, and the most natural way of to represent the numbers in computer system is by a string of bits. We can represent the binary data as a string of bits. Say for example, if we have a plus 6, so 6 is going to be indicated by 0110, and the plus sign will have a 0 4th MSB bit indicating it's a positive number, right? So representation of numbers. Let us consider an n-bit array. Okay, the binary bit p equals to the bit corresponding starts with 0th bit, first bit, and it will be n minus 1 number of bits. As we start with 0, we have n bit vector. So as we start with 0, it will have n minus 1 number of bits. Say for example, the n bit vector value is 4. Then the binary value b will be equals to b0, b1, b2, b3. As we end up with b3, because it has been ending up with n minus 1, so n is 4, 4 minus 1, 3. And if you look at in general, the binary value here, it can be, I value can be ranging from 0 to n minus 1. That value can be either 0 or either 1. Any one of those value we can have. And the value of I will range from 0 to n minus 1. All right. Now, so this vector representation can be made in unsigned integer value as v, and that will range from 0 to 2 power n minus 1. There is a difference between 2 power n minus 1 and 2 power n minus 1. Where we talk about 2 power n minus 1. Say the value of n is 3, or let us say 4, 2 power 4, 2, 4, 8, 16. So 16 minus 1, so that's going to be 2 power n minus 1. So it's 15. Okay. So in that way, if you can able to write this v of b equals to bn minus 1 into 2 power n minus 1 and so on. So this 2 power n minus 1 is the weightage of that. Is the weightage of that corresponding binary value, and the weightage will start from 0. Say for example, see here b0 we have 2 power 0, b1 2 power 1. Similarly, bn minus 1, the weightage is 2 power n minus 1. So in this way we can able to represent both the positive as well as the negative numbers. So how to represent the signed integer? How do we represent a signed integer? We have three different indications here. One is sign magnitude representation. In that we have for one's complement representation and two's complement representation. Okay. So what is this signed binary number or signed magnitude? So we are going to indicate by plus 6, plus 14, minus 14, plus 24, minus 64 and all that. So the sign we are going to indicate 1 bit and magnitude we are going to indicate. So this is signed magnitude. And what about uh, one's complement method? So one's complement method is what? And any drawbacks are there in this sign magnitude? We'll discuss advantages of this. We'll discuss. Just briefly, let us see one by one. This one's complement method of a binary number is the number that will result to you when we change all ones to zeros and all zeros to ones. We have a binary number, you change all ones to zeros and all zeros to ones, that becomes one's complement. And what about this two's complement? This two's complement is the representation of one's complement number plus 1, which means the two's complement is the binary number that results when we add 1 to the one's complement number. To make it short and simple, two's complement equals to one's complement plus 1. So that's how it is. So we can able to represent the two's complement form uh, for negative numbers as well. And what all assumptions we have made here? We have made that we are using 4-bit machine word and we are using 16 different values can be represented because we have 4-bit machine. The 2 power 4 will lead to 16, so we can have a representation of 16 variety of numbers. So if you assume that again roughly half of them are positive and half were negative. Let us assume that we are able to represent a 16 numbers. We can start around from plus 7 to 0 and minus 0 to minus 8. So that way we can able to represent those numbers. All right. So let us continue. So let us understand what is this sign magnitude representation. You see this one here, we are representing by positive sign 0, 1, 2, 3, 4, 5, 6, 7. Up to 7 we are representing here. And after that here minus 0 to minus 7 we are representing. So where the last bit here, MSB bit we call it as, if the bit is 0, the number is plus. If the bit is 1, the number is minus. That's what the difference you can able to spot out easily. So plus 0 will have all zeros, whereas the left side 3 bits will be represented by the magnitude. So 0, 0, 0, this gives you the magnitude here. And whereas the single bit what we have here in the rightmost side, this one will be represented as a sign. This is 0 here. All the numbers we have covered in the right side, all of them starts with 0. So its sign is positive. That's why we represent by plus 6, plus 7, plus 5, all that. And wherein you check these numbers for minus, where we have represented all the MSB bits are represented by 1. So it's very simple. When you have a 0 in the MSB, it's a positive number. When you have 1 in the MSB, it's a negative number. And the remaining lower 3 bits is going to specify the magnitude. If the lower 3 bits are 0, 0, 0, its magnitude is 0. If it is 1, 1, 1, it is 7. So in that way, these numbers will vary from plus or minus to power n minus 1 minus 1. Okay, so this is the complete representation. You can count the numbers. We can able to represent 16 numbers. So 1, 2, 3, 4, 5, 6, 7, 8. Similarly, 8 positive numbers and 8 negative numbers. Totally 16 numbers we can able to represent by using this sign magnitude form. As well as we will continue this one's complement representation next session. All right. So see you in the next session. Thank you.